We've talked about the different elements needed for a substitution reaction. Now let's talk about how solvent will affect the reactions. Organic reactions are usually done in a solvent. And in this case, because nucleophilic substitution reactions start with an alkyl halide and that molecule is polar, we're going to need polar solvents to dissolve the molecules. So for nucleophilic substitution reactions, we will be using polar solvents. But within polar solvents, we will have two subgroups, the protic and aprotic solvents. For the polar protic solvents, they fulfill two characteristics. The first one is that they have dipole-dipole interactions. And the reason for that is because they are polar molecule. Look at water, methanol, that has a CH3OH. Then we have ethanol, terbutanol, and acetic acid. So all of these molecules right here, they display a dipole. And because they have a dipole, then they can have dipole-dipole interactions. The other characteristic is that they have OH or NH bond. In this case, we only see the OH case. So you see, because they have that OH ready, they will be able to have hydrogen bonding. As for the polar aprotic solvents, they are also polar, but the difference now is that they don't have hydrogens available for hydrogen bonding. So if you look at acetone right here, it does have hydrogens. But these hydrogens right here, it has 6 hydrogens, but they are connected to a carbon. And remember that a CH bond is hard to break because if it breaks, then the carbon will end up with a negative charge, and that's not something that the carbon is comfortable with. So it's really hard to break this CH bond, and therefore it's not, so these solvents right here are not able to do hydrogen bonding. So here we have acetone, acetonitrile, THF, dimethyl sulfide, DMF, and HMPA. You should get familiar with these names because I'm going to be using them from now on. So be familiar with the fact that they are polar solvents and that they are aprotic solvents. So let's see how this affects our reactions. Let's start with the polar protic solvents. Remember that the polar protic are the ones that have hydrogens available to have interactions. So to have hydrogen bonding. So for example, imagine that we're using water as my solvent. So you see here you have representations of water, and we want to use Br- as our nucleophile. When you go to a lab, you cannot simply get Br-, so you have to use the species sodium bromide. And when you dissolve sodium bromide in water, what you'll get is the sodium plus the Br-. And now we have to look at how each one of these ions will interact with the water. On one side, in the positive charge ion, what will happen is that it will interact with the electrons here in the lone pair of the oxygen. As for the Br, it will interact with the hydrogens here from the water. So as you can see here in these two images, the sodium will be surrounded and the Br will also be surrounded. Now let's look at a polar aprotic solvent. So imagine I have, again, NaBr, but now I'm using something like acetone. So acetone does not have the hydrogen bonding. So the lone pairs on the oxygen will be surrounding here the sodium, right? Imagine we have it like that. But they will surround the BR, but they will not interact with it. So they will be physically around the BR, but they will not have any type of interaction. So how is that going to affect nucleophilicity? Okay, so when we have a molecule that is small, such as the F minus, what will happen is that in polar protic solvents where we have hydrogens available, they will surround it. So imagine I have here, and I'm just going to say R because it can be anything. So R, R, and R is going to surround it very quickly. Sorry, it's not actually the R, it's the H that is interacting, right? The other way around. So here, R, HR, and HR, right? So the hydrogens are actually interacting with the F minus. And because the F is small, it's going to get surrounded very quickly. Now, if we look at something like iodine that is much, much bigger, you're going to need a lot more solvent for it to get surrounded. So what happens with nucleophilicity? Remember, nucleophilicity is it defines how ready is a nucleophile to go and attack. So if the fluorine is surrounded, it's not going to be able to go and attack. But the iodine minus, because it's so big, it's not going to be fully surrounded. So it's going to be more nucleophilic than the F. So it's very interesting that in the halogens, as we go down and we use polar protic solvents, the nucleophilicity increases. And the reason for that, again, it's because in a larger atom, such as I minus, it's not fully surrounded by the solvent and it still has some of that nucleophilic ability. In the case of aprotic solvents, that is not a problem. And my nucleophile here, going back to the previous example with the NaBr, because the bromine is not actually interacting with the solvent is actually surrounding it, but it's not interacting. It doesn't have hydrogen bonding around itself. It allows the Br to be naked, as we mentioned here, and so the Br is ready to go and attack. So that nucleophilicity issue that we have here in polar protic solvents, it doesn't happen in polar aprotic solvents. So in polar aprotic solvents, where there is no hydrogens to be interacting with the fluorine, with the chlorine, with the Br, with the I, what happens is that the nucleophilicity goes side by side with basicity, which is what we usually expect, because the solvent is not actually interacting with each one of these ions.